A pleasant afternoon, everyone. I hope everyone is doing great and awesome today. And I guess every one of you are very eager to learn new things this afternoon. So I hope you'll be able to participate and we'll listen with our discussions this afternoon. So to start, our objectives this afternoon are we have of course, this afternoon, we are going to explain, or you're going to explain projectile motion in terms of horizontal and vertical components of motion. So another objective that we're going to do this afternoon class is to solve problems involving projectile motion. So now to start, let's have a review first about what we had just discussed last meeting. So we talked about uniform motion and non-uniform motion. This was the highlight aside from the acceleration due to gravity that we discussed last time. So just a recap about uniform motion and non-uniform motion. When we say uniform motion class, what does it mean again? That implies the movement of a body along a straight line with steady speed. So in a uniform motion, there is a steady speed. For a non-uniform motion class, we mentioned that it alludes to the movement of an object along a straight line with variable speed. So to compare the uniform motion from a non-uniform motion, uniform motion is it is along with a straight line with steady speed, while in a non-uniform motion, it is along a straight line with variable speed. Another difference between the two, in a uniform motion, it covers equal distances in equal time. So there is an equal distances. So I highlight the word equal distances. On the other side, in a non-uniform motion, it covers unequal distances. So they're really different from each other in equal time interval. So again, uniform motion covers equal distances. Non-uniform motion covers unequal distances. So I hope you can follow. Another thing also, uniform motion is similar to actual speed of the object, while non-uniform motion is different from actual speed of the object. So now, talking about the distance time graph, the distance time graph in a uniform motion shows a straight line, while in a non-uniform motion, the distance time graph shows a curved line. So that's the difference between the two when we talk about the distance time graph between a uniform and non-uniform motion. And lastly, in a uniform motion, we always remember that in a uniform motion, it has always zero acceleration, while in a non-uniform motion, it has a non-zero acceleration. So we differentiate between the uniform motion and non-uniform motion because our topic this afternoon will be related to these types of motion, especially in a non-uniform motion, where it will give us a curved line in a distance time graph. So are you ready? I hope everyone is ready. I guess you have the idea about our topic this afternoon. Why don't you try a guess? Tell me, what do you think is our topic this afternoon? I can see it in your eyes that you can relate what is our topic this afternoon. Yes, it is all about projectile motion. So if you have a guess about projectile motion, then you are correct. So our topic this afternoon, as what I said, is something related to projectile motion. But before anything else, we have key terms that we need to be familiar of in this topic. What are these key terms? So let's start with projectile object. What is projectile object class? When we say projectile object, as you can see there, it is a moving through the air. Again, when we say projectile object, these are objects moving through the air, either initially thrown or dropped, subject only to the effects of gravity. So that is how we define projectile object, moving through the air. It's either initially thrown or dropped, which is subject to the effect of the gravity. So that is a projectile object. Next term or key terms that we have to be familiar of in this subject, or in this topic rather, is about the word trajectory. So what is trajectory, class? When we say trajectory, this is a path. So this is a path of a projectile. Again, trajectory is the path of a projectile, which is parabolic in 2 dimensions. Again, trajectory is the path of a projectile, which is parabolic in 2 dimensions. So that's the meaning of trajectory. It's different from the word projected because sometimes we interchange the concept between the two words, projectile and trajectory. They are different, okay? Though they are related. So now, next or lastly, we have to be familiar of the word or term projectile motion. As I mentioned a while ago, our main concern this afternoon about projectile motion. So when we say projectile motion, class, it is the movement of an object through the air. Again, movement of any object through the air. So I'll highlight the word air, through the air. Subject only to the effects of gravity. So there is an effect of gravity, or gravity is a factor in a projectile motion. So again, do not forget the key terms that we have to be familiar of this afternoon: projectile object, trajectory, and projectile motion. I hope you can now differentiate or can define or describe these 3 terms that I just mentioned. Okay, so I guess we are now ready for the next slide. So what is now projectile? What did I say? What is projectile? So as I mentioned a while ago, we can also describe a projectile as any object which projected by some means and continues to move due to its own inertia or mass. So we can illustrate a projectile in this given illustration. So as you can see, that is an example of a projectile or a projectile motion. You can see there is a trajectory in it. So next, now let's try to know or determine projectiles, about the dimensions rather of projectile motion. So projectiles move in 2 dimensions. Again, projectiles move in 2 dimensions. So what are the movements? So since a projectile moves in 2 dimensions, class, it therefore has 2 components, like vectors, correct? Just like a resultant vector. Again, since a projectile moves in 2 dimensions, it therefore has 2 components, just like a resultant vector, if you could still remember. So the 2 components that we have, or 2 dimensions in a projectile motion, we have the horizontal and vertical components. So again, a projectile motion has, or the movements of the projectile motion has 2 dimensions. What are those? We have the horizontal component and vertical component. So I hope you can just describe it there. As you can see, the red arrows, it shows vertical component. So the the blue arrows, it shows, the blue arrows rather show the horizontal component, or yeah, horizontal component of the result of the vector, or of the projectile motion rather. Okay, so horizontal velocity. Now let's talk about the horizontal velocity component. So in a horizontal velocity component, we can describe in here that it will never, or it never changes. Again, in a horizontal velocity component, it never changes. Take down note of that. It covers equal displacements in equal time periods. So what does it mean? This means that the initial horizontal velocity is equal to the final horizontal velocity. Again, I'll highlight, in a horizontal velocity component, it never changes. It covers equal displacements. That means the initial horizontal velocity is equal to the final horizontal velocity. That is how we describe the horizontal velocity component. So another thing also that we can describe in here, as you can see, 1 meter per second is equal to 1 meter per second. That means that the initial horizontal velocity, which is 1 meter per second, is equal to the final horizontal velocity, which is also 1 meter per second, as you can see in the, or based on the illustration, this one. Okay, so are you still okay? So I hope you're still okay and you can still follow. I guess you can follow about this. So in other words, class, the horizontal velocity is constant. But why? Why do you think it's constant? Anybody? Try to think about it. We know that the initial horizontal velocity is equal to the final horizontal velocity under the horizontal velocity component. So why is it that the horizontal velocity is constant? What's the reason? Try to think about it. So actually, the reason is there. Gravity does not work horizontally to increase or decrease the velocity. You can relate that one. Try to imagine about this one. Correct? So again, the horizontal velocity is constant because the gravity does not work horizontally to increase or decrease the velocity. So I hope you can imagine that one and you can relate with that. So very clear. So next, now, after talking about the horizontal velocity component, we will now talk about the vertical velocity component. So in a vertical velocity component class, so in here, we can describe, or these are changes due to gravity. That means it does not cover equal displacements in equal time periods, unlike in a horizontal velocity component. Again, I'll repeat, in here, or in a vertical velocity component, it changes due to gravity. Unlike in a horizontal, it does not change. In here, it changes because of gravity. And it does not cover, so there is no equal displacements in here. So it does not cover equal displacements in equal time. So that is the difference between a horizontal and vertical velocity component. Again, in a vertical velocity component, changes due to gravity does not cover equal displacements in equal time. So I hope you can, and you can remember that one, as you can describe in the illustration. So as you can see, a 5 meter per second, our start when it falls. Then next is from 20 meter per, okay, 20 meters rather. And then we have 45 meters. So it is increasing. So how do we describe the illustration? We can describe it as as this. Both the magnitude and direction change. Again, in a vertical velocity component, both the magnitude and direction change. So I'll highlight the word, I underlined the word magnitude and direction. They will change. Both will change. Remember this one. As the projectile moves up, the magnitude decreases. Again, as the projectile moves up, what will happen? The magnitude decreases. And its direction is upward. So not forget that one. When the projectile moves up, the magnitude decreases and its direction is upward. Another thing also in here, as it moves down, the magnitude increases and the direction is downward. So do not forget that one under the vertical velocity component. So once the projectile moves up, what will happen to the magnitude? It decreases. The direction is upward. So when it goes down, what will happen? In the vertical velocity component, the magnitude increases and the direction is downward. So I want you to remember that one, a very important concept under vertical velocity component. So let's now proceed. So let's now proceed to the horizontally launched projectiles. So let's try to describe how horizontally launched projectile is. So these are projectiles which have no upward trajectory and no initial vertical velocity. Again, in a horizontally launched projectiles, I want to highlight this one. These are projectiles which have no upward trajectory because it's horizontal. So no upward trajectory and there is no initial vertical velocity because it is horizontal. That's why there's no upward trajectory and there is no initial vertical velocity. So I want you to take the note of that. So as you can see there, so you have it in the based on the illustration, it shows that there is no, in a horizontally launched projectiles, there is no upward trajectory and there is no initial vertical velocity. So look at it's 0 meter per second, the vertical velocity. That's why there is no initial vertical velocity in a horizontally launched projectiles. So that means initial vertical velocity is 0 meter per second. Another thing also, the V, this shows or this gives us the idea about the initial velocity along X component or horizontal line. And this one is the final velocity along X component or horizontal line. That means that they are equal, meaning to say they are constant. That means also that the initial horizontal velocity, V sub OX, is equal to the final horizontal velocity. That's why they are constant. Again, I'll repeat. In this illustration, it shows that the initial horizontal velocity is equal to the final horizontal velocity. So I hope you can relate about this one. And the next is under also in a horizontally launched projectiles, we have it here. To analyze a projectile in 2 dimensions, we need 2 equations. Again, to analyze a projectile in 2 dimensions, we need 2 equations. One for your X direction and one for your Y direction. So how do we analyze the projectile in 2 dimensions? Based on the 2 equations or based on the equation. What equation that we can use? Again, we can use the equation of motion or the equation of kinematics or kinematic equation. The equation number 3. Remember this equation? Okay, S is equal to UT plus 1/2 AT squared. So in that equation, in the equation of motion, we can now let your ut or your x component as x is equal to ut. So you can let your, or you can have the equation of your x component as ut is equal to ut rather. So, and also for your y component, you can have the equation of your y component as 1/2 AT squared. Now, question why? Why is it that the x component has the equation of ut based on the equation of motion? And y is equal to 1/2 AT squared. So here's the explanation. X component is equal to ut because remember, the velocity is constant horizontally. X is a horizontal line, okay, or horizontal component. So meaning to say, remember that the velocity is constant horizontally. That means that the acceleration is 0. That's why 1/2 AT squared becomes 0, because the acceleration is 0 since the velocity is constant horizontally. That's why your x component has the equation of x is equal to ut, as I encircled. So why is it that your y component has the equation y is equal to 1/2 AT squared? Because remember that since the projectile is launched horizontally, the initial vertical velocity is what? Is, okay, sorry, for a while. So again, the initial, so we have it 1/2, or your y component is 1/2 AT squared, because remember that since the projectile is launched horizontally, the initial vertical velocity is 0. Okay, so I hope you can follow. Again, the equation for your x component is equal to ut, and the equation for your y component is 1/2 AT squared. So I hope you can follow. So let's now proceed or describe the vertically launched projectiles. So in a vertically launched projectiles class, always remember no vertical velocity at the top of the trajectory rather, as you can see there. No vertical velocity at the top of the trajectory. So based also on the illustration there, vertical velocity decreases on the way upward. Again, vertical velocity decreases on the way upward. And of course, the horizontal velocity, as I mentioned a while ago, it is constant. And the vertical velocity also increases on the way down. Okay? So do not forget, no vertical velocity at the top of the trajectory. And vertical velocity decreases on the way upward, and it increases on the way downward or down. And also for the horizontal velocity, it is constant. So based on the illustration. So I hope you can still follow, class. So we can summarize this one in this context. Component for the horizontal component, the magnitude is constant, and the direction is also constant. Under vertical component, as you can see on the table, so in vertical component, we have here the magnitude decreases up, 0 at top, increases down. Again, it decreases up and it increases down. So that's how we describe, and 0 at top. So no vertical velocity at the top of the trajectory. That's according to its magnitude. And for the direction, vertical, in a vertical component, direction changes. So do not forget that one. We can summarize it in that way. So now we don't have much time. Let's go right away to the, so vertically launched projectiles, since the projectiles was launched at an angle, the velocity must be broken into components. As you can see, remember the vectors, the vector quantities. So we have it there as the resultant, V sub O. We have the horizontal component, which is your V sub OX. This one, horizontal component. and also the vertical component. And this V sub O is your resultant vector. So if you want to look for your horizontal component, you can use the formula V sub OX is equal to V sub O times cosine theta. And if you want to look or find for your vertical component, you will use this equation or formula, which is V sub OY is equal to V sub O times sine theta. Theta here is your given angle. I guess we discussed this one, so you know how to use this one already, the Pythagorean theorem, or yeah, principle. So now, in a vertically launched projectiles, these are several things you must consider when doing these types of projectiles. Besides using components, if it begins and ends at a ground level, again, I'll highlight, if it begins and ends at ground level, the y displacement is 0, or y is equal to 0. As you can see, when it begins and ends at the ground level, then the displacement now becomes 0, or y is equal to 0. So now, let's now go to our application about the concept that we just talked about. So now let's try to answer this example number 1. A stone is thrown horizontally with a velocity of 12 meters per second from the top of a vertical cliff. So calculate how long the stone takes to reach the ground 40 meters below and how far the stone lands from the base of the cliff. So I want you to read the example. Example 1. Okay, I'll give you time to read it. Okay, now let's solve it together. So step 1, we have to consider the ball's vertical motion. It has a 0 initial speed vertically, we know that, and it travels 40 meters with acceleration due to gravity, which is 9.81 meters per second squared. Again, it travels 40 meters and it has 0 initial speed vertically. So next, let's continue. So we use the formula S is equal to UT plus 1/2 AT squared. Remember that equation? And then we will just substitute, replace S, since it travels at 40 meters, so we have it 40, is equal to 0 plus 1/2, 0 because the initial velocity is 0. Or yeah, since it is initial speed vertically. So that's why it's 0. So plus 1/2 times 9.81, which is the acceleration due to gravity, times t squared. Again, we just substitute the given to the equation. So it gives us 40 is equal to 4.905 t squared. Then divide both sides by 4.905, and that gives us t squared is equal to 40 over 4.905. Then that gives us 8.15439. So we'll get the square root of it. And then to get your time. So t now is the square root of 8.1549439. That gives us 2.855686 seconds, or we can just round it off into 2.86 seconds. So our time now is 2.86 seconds. So next, step number 2, consider the ball's horizontal motion. So the ball travels with a constant horizontal velocity, which is 12 meters per second. So as long as there is no air resistance, then the distance traveled is equal to u times the time, which is equal to 12 times 2.86. So next, that gives us, when we multiply 12 times 2.86, that gives us 34.3 meters. So our distance traveled is 34.3 meters and the time is 2.86 seconds. So you may also find it easier to summarize the information like listing all the given. Like for vertically, we have S is equal to 40, U is equal to 0, A is equal to 9.81, then find your time, your t, and then your v, or your distance traveled. Okay, so another thing also for horizontally, you may also have it u is equal to 12, v is equal to 12, a is equal to 0, then time is missing, and then s is missing. So you can do the same thing. So to make it easier for you to summarize the information and to solve the problem. Okay, so I guess it's already time for you to do your activity. So if you have some questions, class, you feel free to ask me. Okay, I will just be here again to entertain your questions or your concerns. So you can just do your activity now, and hopefully you can make it, or you'll be able to finish it before that time. Okay, so have fun solving. So I'm giving you the activity to solve and to apply these concepts that we just talked about. Okay, thank you for listening. Thank you for listening.